All right, here we are for AP Physics impulse momentum problems. Let's try problem one. How quickly can you set the Earth moving? Estimate the recoil speed of the Earth when you jump up as high as you can, pushing off it. In your solution, list the quantities used as data and the values that you measure or estimate for them. So here we go. So the idea is that, you know, you will be standing on the Earth as one does, right? And the idea is that if you jump upward, then of course you're going to push off the Earth. Oh, no, look, that's the Earth. You'll push off the Earth, right? And you will gain some momentum going upward, right? So you will gain some momentum that way. And the Earth will need to gain an equal and opposite amount of momentum that way, because if I treat them as one combined system, there is no outside force, no outside impulse on them. So the total change of momentum for the Earth-person system is going to be zero. So whatever momentum they gain up, the Earth gains the same amount down. And so that's the sort of calculation we're going to do. So we're going to say my system, here for number one, is going to be person and the Earth. Okay, and we're going to set up our impulse momentum calculation. FDT, our impulse is the change in the momentum, but the impulse is zero because there's no outside force on our combined system. And so 0 is delta P, and that means that the initial equals the final. And so if I add up all the initial momenta and add up all the final momenta, they would be the same thing. So at the start, the momentum is 0, everything's sitting still, and then you jump off. And so there's going to be the mass of the person times that that velocity of the person when they jump up, plus the mass of the Earth times the velocity of the Earth recoiling away from you, right? And this is what we're trying to find. And so you say, well, I got to know the mass of the person, mass of the Earth, and the velocity that that person jumps off with, right, takes off with. Now that takeoff velocity, I'm going to find that one through some kinematics. A v naught v delta xt, right? And let's say that you if you jump up, that initial velocity you jump up with, you say our acceleration is going to be negative g, right? Now, so here's what I'm going to do. I know that if I jump up in the air, all right, my goal is to find out that velocity that I take off at, right? That momentum I get pushing away from the Earth, so I know what the Earth recoils at. And so you say, well, I'll figure this out based on knowing that if I jump up in the air, that at the peak, my speed will be 0. This is a person, and we're going to go from, is my system, and we're going to go from ground to peak here, right, of the jump. And so trying to find this initial velocity. So if I knew the time I was in the air up to the peak, or if I know how high I can jump, then I'll have a pretty good idea of what my initial velocity would be, right? I could calculate that out. Let's see, how much can I jump? Now, when you jump, you kind of crouch down, but what I really care about is like how high I can lift my center of mass, like lift my belly button from a standing position. And I don't think I'm going to be able to lift it more than a meter in a jump. I don't think I've got a vertical jump more than a meter of me. Let's just round it off. We're going to do an estimate in here anyway, right? We're going to estimate the recoil speed of the Earth. Let's just say that you can jump up 1 meter. Okay, lift your center mass up a meter when you jump. So let's round that to -10. Make the numbers easy for us. So let's see here. I want the v squared is v naught squared plus 2a delta x. There we go. It's going to be the root of 20, right, is my v that I take off at. That's the velocity of the person there. I don't know. I feel like I could have made that a little bit easier. Now the mass of the person, let's just round it off and say a person's around 100 kilograms. Okay, that's like 224 pounds or something. I'm obviously overestimating. Let's just say 100, right? I think that's right. 100 kilograms. I think that's like 220 pounds or something. You know, the good news is this can be easily looked up on Google, right? And so you can say, and Google tells me 100 kilograms is like 220 pounds. Hey, how about that? And I think the standard adult human is like 185 pounds or something, if I remember right. 180, something like that, or 85 kilograms or something. Anyway, let's just say 100. Round it off, right? Round it off. We're estimating, okay? So 100 times root of 20, which I probably could estimate easier. Then the mass of the Earth, that's like 6 times 10 to the 24 kilograms, right? And so if I rearrange this, it's going to be like 100 times the square root of 20, and then I'm going to divide that by the quantity, just divide by 6, okay? And I get 74.5, and then times 10 to the negative 24. So you say, so yeah, so it's about like 7.5 times 10 to the negative 23 meters per second. And you say, hey, good grief, that's ridiculously small recoil velocity for the planet. You say, well, of course, the Earth is immense, right, compared to the mass of the person, right? And you say, so yeah, it's a teeny tiny. Are you even going to be able to measure this? Well, I mean, this means that in a second you would go this far. Do you remember that, like, the radius of like a hydrogen atom is something like, isn't it like angstrom or something, an angstrom and a half? Isn't it like 10 to the minus 10 meters? This is like, what is that? If it's like 10 to the 12 times smaller, what's that going to be? You say, well, gosh, that's like 10 to the 12. That's like a trillion times smaller than the width of the radius of a hydrogen atom. You're like, yeah, that's nothing. That recoil is so small, you're not going to notice that. But you say, if I ran through the whole thing, you say you would take off, the Earth would recoil away, right? But you're attracting to each other, and that force trying to pull you together would slow you down and then bring you back to where you were, right? Back together again, right? Okay, and obviously you're going to shift way more than the Earth will, but you are really kind of pushing off each other, then attracting back down. You're going to end up right back where you were, back where you started. There's no outside impulse to change the overall momentum of the system. Okay, so that's problem one. So I estimated using 100 kilograms for the person. I did go ahead and cheat and use mass of the Earth is actually like 6 times 10 to the 24 kilograms. I'm pretty confident that's the right value. And then I assumed that I could jump up, that my max height in a jump was around 1 meter. Those are the values I used to solve this. They were just estimates. Okay, that's problem one.